3 is on sampling distributions and estimators. And there are three types of estimators, right? We have proportions, means, and variances. The proportions, for the proportions, the sample proportion, p hat, estimates the population proportion, p. Right, so we have our sampling procedure. We randomly select n values and find the sample proportion, p hat, for each sample. And we have a whole bunch of these, right? We do it whatever number of times. And because of that, we obtain ourselves several different sample proportions. They could be slightly different. They could be relatively close to the same, and as such, because they can be different values and whatnot, they do obtain a distribution of the sample proportions. And if we were to graph out all of the potential sample proportions from these, we would see it leads to a normal distribution. For the means, we have the sample mean, x bar, estimates the population mean. Estimates the population mean, mu. So again, we randomly select n values and find the sample mean for each sample. We have multiple different samples based upon the number of times we do it. And because of that, we have a whole bunch of sample means. And in those sample means, if we were to see how they distribute around what the mean should be, this also gives us a normal distribution. The variances, the sample variance s squared, this estimates the population variance, sigma squared. So we would randomly select n values and find the sample variance s squared for each sample. Again, we do this a whole bunch of times. We have a whole bunch of samples, a whole bunch of sample variances. But now, this particular distribution, this is not a normal distribution. It is indeed a skewed distribution, as noted on here. And this particular skewed distribution does have a fancy schmancy name attached to it, which is noted as the F distribution, but we'll talk more about that during a later actual lesson. For the time being, though, just point out that it's skewed. Anywho, for the sampling distribution of a statistic, the distribution of all values of the statistic when all possible samples of the sample size n are taken from the same population. The format is in a probability histogram, formula, or table, as we have seen with probability distributions. The three types, as I said, were sample proportion, p hat, sample mean, x bar, and sample variance, s squared. For the sampling distribution of the sample proportion, this is the distribution of the sample proportions p hat with all samples having the same sample size n, taken from the same population. P is the population proportion and p hat is the sample proportion. The behavior, though, of the distribution of sample proportions tends to approximate a normal distribution. So we would then say it's approximately normal. Approximately normal. And as you could assume, we have a procedure to verify it's supposed to be approximately normal. Likewise, sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions p hat is equal to the population proportion p. And again, there's a bunch of mathematical ways to show that, but that's what that means. An example, though, that does kind of show it is consider repeating this process, rolling a die 5 times. Find the proportion of odd numbers, 1, 3, or 5. What do we know about the behavior of all sample proportions that are generated as this process continues indefinitely? Well, if you look at all 6 sides of the die, there are a total of 3 of those that are odd. I have a total of 6 sides. So 3/6 is the population proportion, or if we want, we can reduce that to 1/2, or 0.5. Right? And if we repeat this process 1,000 times, 10,000 times, and if we repeat this process 10,000 times of, finding the sampling of rolling the dice 5 times, find the sample proportion each time we generate 10,000 samples, and we obtain 10,000 sample proportions, some of which are the same, some of which are different, we would obtain a histogram of the distribution of the sample proportion. And notice that the distribution of the sample proportion becomes approximately normal. So the behavior is that this is approximately normal. Now I know it's hard to tell this by just looking at a graph, or in this case this histogram down here, but if we attempted to find the mean of this distribution of the sample proportions, we would find that the mean of those sampling distributions, so mean of the sampling distribution of the sample proportion, this would also be equal to 0.5, which is the same thing as what that population proportion was. So as long as it's approximately normal, whatever that population proportion is the mean of the sampling distribution of p hat. For the sampling distribution of the sample mean, the distribution of all possible sample means x bar, with all samples having the same sample size n taken from the same population. Just as with the sample proportion, the distribution of all sample means tends to be a normal distribution, and the sample means target the value of the population mean. So the same idea, a pediatrician has 3 patients with measles, and their ages 4, 5, and 9. Consider the population of 4, 5, and 9. If 2 ages are randomly selected with replacement from the population of 4, 5, and 9, identify the sampling distribution of the sample mean by creating a table representing the probability distribution of the sample mean. Do the values of the sample mean target the value of the population mean? Well, we first kind of need to know the population mean for 4, 5, and 9. If we average those three numbers, the mean of that is 6.0. Okay? We can see that because this adds up to 18 divided by 3. Hence where that comes from. But anyhow, so that gives us a value of 6. And we could see that we have the different samples of taking two ages for each one of these. So 4, 4, 4, 5, 4, 9, 5, 4, 5, 5, 5, 9, 9, 4, 9, 5, and 9, 9. The sample mean then just takes by averaging each of these samples to get 4, 4, 4, 4.5, 6.5, 4.55, 7, 6.5, 7, and 9. And this has a probability of 1/9. Since we would get repeats in some of these things, we could condense it a bit to this table down here. And if we were to take the sample mean of this, table down here, we would also find that the sample mean from this is also equal to 6. So, because of this, the sample mean targets the population mean. And because of that, these two means are the same. The sampling distribution, the sample variance, the distribution of the sample variances, so s squared, with all samples having the same sample size n taken from the same population. The behavior is that the distribution of sample variances tends to be skewed right. And the sample variances target the value of the population variance. And with example 3, you consider repeating this process again 10,000 times. We're only going to type 5 times and find the variance, s squared, of the results. What do we know about the behavior of all sample variances that are generated as the process continues indefinitely? So again, we do this 10,000 times. If we were to find the variance of the values from the die of 1 through 6, the variance, population variance, would be 2.9 if we did that calculation out. This sample variance, do it 10,000 times, so 10,000 samples, find 10,000 variances, sample variances. We obtain a distribution that looks like this. Again, it's kind of like an F distribution, but not a perfect one per se. But the whole idea of it, though, is that this distribution has sample variance of 2.9. Which again, these are the same. So we know the sample variance targets the population variance. And an estimator is a statistic that can be used to infer or estimate the value of a population parameter. An unbiased estimator is a statistic that targets the value of the corresponding population parameter, where the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter. This happens with the population proportion p hat, the sample proportion p hat, sample mean x bar, and the sample variance s squared. A biased estimator is a statistic that does not target the value of the corresponding population parameter, that being the median, range, standard deviation s. Although, for relatively small bias and large samples, we can estimate the population standard deviation by the sample standard deviation. Just as an example 2, we want to consider samples of size 2, randomly selected from the population of 4, 5, and 9. We want to list the different possible samples along with the probability of each sample and find the range. So if you remember from that table, we had 4, 4, 4, 5, 4, 9, 5, 4, 5, 5, 5, 9, 9, 4, 9, 5, and 9, 9. If we want to take the ranges, so subtracting these, we get 0, 1, 5, 1, 0, 4, 5, 4, 0. And the probability of these occurring is 1/9 for each one of them, since they're all equally likely. And so for A, it's just this table here that I just drew. For B, we want to describe the sampling distribution, the sample range, in the format of a table similar as in the probability distribution. Well, to put that frankly, this is part A. As you can imagine, the textbook likes to repeat itself. Based on these results, do the sample ranges target the population range of 5? The answer to that is no. No, and that's because the mean of the sample ranges is 20 divided by 9. If we were to add up all this entire column, 20 divided by 9, this gives us an answer of about 2.2. So no, it does not. And then what do these results indicate about the sample range as an estimator of the population range. This is a biased estimator because of it. Thank you.